Okay, so now we want to talk about a couple other ways to help us do counting, and that is permutations and combinations. So permutations are a small extension of the fundamental counting principle in the context where order matters and where repetitions are not allowed. Now later on you can like adjust this a little bit to allow repetitions, but we're not doing that right now. So we're going to start out with the basic permutations. So, and a great example of this is like if I'm doing horse racing and I have 7 horses, right? And so, and again, order matters in horse racing, so it matters who comes in first, second, and third. And so I have these 7 spaces. If I think about how many possible ways there are for a horse to come in first, if I have 7 horses, there's 7. But then for the second possible space, I can't have 7 horses anymore because one of them already came in first. So I have 6 horses that can come in second, 5 horses that can come in third, 4, 3, 2, 1. And this sort of structure where I'm multiplying, right, because I'm using the fundamental counting principle to count how many total outcomes, where I'm multiplying together, occurred so often in probability that people gave this a special notation, and it's called the factorial notation, and that's 7 factorial, right? So it's 7 times 6 times 5 times 4 times 3 times 2 times 1, all the way down to 1 is called 7 factorial. Okay. So that's just kind of a very straightforward permutation where I have 7 objects and I want to order and care about the ordering of all 7 of them. Now, a lot of times in these problems, I don't care about the order of all 7 of them, and in particular in horse racing, I only care about, let's say, the first 3 items. And so I want to get there was a lot of interest in getting an algebraic expression for something that would give me this, just 7 times 6 times 5. And we have this factorial expression. And it turns out like 7 times 6 times 5 is really close to 7 factorial, except it's missing some things. And I want to like strategically remove this 4 times 3 times 2 times 1 and be able to kind of calculate this or have this shorthand notation for what this means, right? So I really start with this kind of 7 factorial idea. It's really because the second expression is really close to that. And if I picture that 7 factorial in this kind of added on to this yellow piece, and I have like times 4, times 3, times 2, times 1, what I really want to do, because those items are multiplied, is one way to get rid of them in like through algebra is to divide by them. So these two expressions, like this yellow just 765 and this expression I've written, are equivalent, right? But the advantage of that is the top is 7 factorial and the bottom is 4 factorial. So they can be written really, really straightforwardly. And really, I get 4 items on the bottom because I just want to count the first 3. So that's 7 minus 3 tells me how many of these red items are left over. But that's 7 factorial over 4 factorial. So it's just a much shorter way to write the stuff that's kind of all multiplied together. Okay, so really I have permutations is NPR is the shorthand notation, N representing the total number of items that you have to choose from, and R is the number of things that you're actually interested in. So when I do NPR, like in the previous problem, I was doing 7 pick 3. Right, I had 7 horses and I only cared about 3 of them. But in general, NPR is n factorial. The formula for it is n factorial divided by n minus r factorial. And that gives me the number of permutations of r items out of a group of n, right? So if I had 10 pick 3, that would be 10 factorial all over 10 minus 3 factorial. Okay. And then I could figure out what that was, and it's really not that hard. You can, I mean, That's really the same thing as 10 times 9 times 8. 9 times 8 is 72, times 10 is 720, right? So again, these are counting. Permutations give me a count. They don't give me probabilities. They just give me a count. So I'm counting here like the total number of possibilities. This would be a number in the denominator usually. Okay. So if I start looking at a couple of these other problems, like permutations are used for these problems where like I have two people running, let's say in a school club, and they're running for president and vice president, and like whoever gets the most votes gets president, and whoever gets the least votes gets vice president. So this is just 2 times 1, right? I have 2 possible spaces, and there should be 2 total outcomes. But this is also a permutation, right? It's the number of ways to order 2 people, and is 2 pick 2, right? I have 2 people. If I have 3 people, now I have 3 times 2. And that should give me 6 total possibilities. That's 3 pick 2. And then if I have 4 people, it should be 4 pick, I'm still just picking 2 people, right? So this is kind of permutation. So then if I had more people, like if I had 10 total people and I wanted to pick 3 spots like president, vice president, secretary, it would be 10 pick 3. Okay. So that is permutation. So when we move on, combinations is again a little bit of a step further. In permutations, I really care about order. Order really matters. In combinations, order does not matter. Repetitions are still not allowed, but I don't care about order anymore. So I have, like, an example of this is for poker hands, where I don't really care what order I was dealt a king in, or if I have 4 aces, I don't care which one came first. I just care that I have a group of 4 aces. So these are great for probability problems that involve just like groups of things. Okay, so let's say that I have 20 students and I want to pick a group of, let's say, 4 of them to do jobs around the classroom. And you know what? I think 4 is going to be too many because I want to look at a smaller problem. But that would be an example of 20 choose 4. I don't really care. That's just a group. But I don't really care what order I'm picking them in, right? Okay, but I want to look more specifically at this maybe for a smaller group so we can see how the permutation formula changes into the combination formula because they all build on each other. The fundamental counting principle builds on just tree diagrams. The permutation formula builds on the fundamental counting principle, and the combination formula builds on the permutation formula. So let's do 20, choose 2. Let's just say I need 2 kids to do something. And I'll look at this smaller problem, right? Okay, so, and if I was going to calculate permutations, I would do 20 factorial over 20 minus 2 factorial, and that's 20 factorial over 18. It would be 20 times 19, whatever that is, right? Like 380. Okay, but let's say, but I want to go to this place, but that involves order. And if I'm going to this place where order doesn't matter, then like if I'm picking Mary and John, and if I'm picking John and Mary, like under permutations, those count as 2 different ordered lists. And now under combinations, I don't care that what order they're in. I just care that John and Mary are in a group together, right? So I had 2 things that were counted under permutations, and now I just want to count them as 1. So if I have this permutation number, this 380 total possibilities for NPR, really I would divide that by 2. So divide 380 by 2 and get 190. And that would be the total number of combinations that I had. So let me get a new slide here, and I'm gonna try. I need to turn this into a blank slide, so let me do that real quick. Okay. So if I had two items, then I was going to divide by 2, right? To move from the number of permutations of the 2 items to the number of combinations of 2 items. So if I have 2 items and I permute them, there are 2 ways to order that list. That's John, Mary, and Mary and John, right? But under a combination, I'm just thinking of them as one group um, that's just John and Mary together. I don't care what order they're in. Now, if I have 3 items, let's say Mary, John, and Abraham, right? So Mary, John, and Abraham, and I list all the ways there are to order these. So I go back to the list, and I'm just kind of trying to think through what I have to do to this permutation formula to change it. So I could get Mary, John, Abraham. These are very Bible-centric names, I'm realizing. Mary, Abraham, John. John, Mary, Abraham. John, Abraham, Mary. Abraham, Mary, John, Abraham, John, and Mary, right? And there are 6 total possibilities um, for the ways to order 3 items. And really, those 6 permutations, that's what they are going to just turn into one group in combinations, right? So here I have to divide by 6. I don't really care what order these 3 people are. I just want a group of 3 people. So I would divide by 6. But this kind of makes sense because this list is the number of ways to order 3 items. It's the number of permutations. It's 3 times 2 times 1, right? So, and that's 6. So when I go to 4 items, I mean, you can do this sort of experiment again and list them all out. I won't because 4 items has quite a few possibilities. It really should be 4 factorial that I have to divide by to go from the permutation formula to the combination formula. So in the same way that I had to divide that fundamental counting principle to get rid of something that I didn't want, in combinations, I also have to divide the number of permutations by something, by this extra factor. So there's the permutation formula, n factorial over n minus r. The combination formula is the same, except I'm going to also divide by this little r factorial, the number of things that I'm interested in, the number of things that I care about, because that tells me how many copies that I get under the permutation formula, right? So these are these 3 formulas. So if I had 20 choose for, then it's 20 factorial, and then 20 minus 4 factorial over 4 factorial, right? And that's like my original problem. If I had 20 kids and I need to choose 4 of them to do a job, I would calculate this, and it would give me that under a group that's not ordered. Okay. So then I want to do one more problem and just give you an example of these combinations in kind of application. So let's do this poker hand. There's 52 cards in a normal poker deck, and let's say we're playing 5-card poker, so I have 5 cards in my hand. And I just want to count the total. Again, we're counting. These are not probabilities yet. We're going to get into probabilities the next time. Just counting. So count the number of total poker hands there are. Right? And again, I don't care about order, but I do know that repetitions aren't allowed. Like I can't have the ace of diamonds in my hand twice, right? So this is 52 choose 5, and I get that by doing 52 factorial over 52 minus 5 factorial, and then times 5 factorial in the denominator. And I'll show you how to cancel these so you know how people do these by hand. So this is 52 factorial over, and then I'm going to get 47 factorial over 5 factorial. And then this 47 factorial is really hidden in the 52, so people will write out the first few pieces of this 52 factorial so they can cancel with the 47, so they'll just write it out until they get down to 47, like right here. And then I'm going to put a factorial because that matches the denominator, and I kind of know where I'm going, right? So I get 47 factorial, and then those cross out, right? And I get rid of all these lingering kind of trailing pieces. And then I'll write out the 5, 4, 3, 2, 1 and do as much canceling as I can with the top. So the 5 should cancel with the 50 and leave me 10. The 4 should cancel with the 48 and leave me 12. The 3 will cancel again with the 12 and leave me 4. And then the 2 should cancel with the 4 and leave me 2. And then I'm just left with 52 times 51 times 10 times 49 times 2. And this should always cancel everything in the bottom because these are whole number answers. And then if I multiply that out on my calculator, let me see what I get. $2,598,960 total possible poker hands. Okay, so again, this is not a probability. This would just be the denominator in a probability problem that we'll look at next time, which is like how many ways, what's the probability of getting 2 kings in your hand or things like that, right? But I have to know the total possible poker hands to figure that out. Okay.